US Physics Olympiad, year 2013, F equal MA. First round. For the first round, that was given 25 problems, and for that it was given 75 minutes. All solutions for all these problems you can find below this video in the reference of the description. Problem number 1. An observer stands on the side of the front of a stationary train. When the train starts moving with a constant acceleration, it takes 5 seconds for the first car to pass the observer. How long will it take for the 10th car to pass? Solution. Here we can use a kinematic equation which connect distance with time, with the initial zero speed. That will be this one. Let's T1 will be the time to pass first car through observer. The length of the first car will be 1/2 a T1 square, where a is acceleration. Same thing we can say for pass of 9 cars and pass for 10 cars. So that will be second and third equation. Now we can divide the third equation by first equation and the second equation by first equation, which give us these two relations. T10 over T1 square equal 10 and T9 over T1 square equal 9. Now we can express T10 and T9 through T1 and subtract for 9 cars to pass observer from 10 cars time 10 cars to pass observer. That will be total time to pass car number 10. And finally we have 0.81 seconds, which is answer E. Problem number 2. Georgie stands 20 meters from a wall and Diego stands 10 meters from the same wall. Georgie throws a ball at an angle of theta equal 30 degrees above the horizontal, and it collides elastically with the wall. How fast does Georgie need to throw the ball so that Diego will catch it? Consider Georgie and Diego to be the same height, and both are on the same perpendicular line from the wall. Solution. In these circumstances, behave like a mirror for elastic collisions. It means that equivalent distance between Georgie and Diego is 30 meters. And here we can use formula for range. Distance equal v square over g multiplied by sine double theta. And from here we can find what is the speed. V square equal d multiplied by g over sine 2 theta, or after putting numbers we have finally speed equal around 90 meters per second. That's the answer C. Problem number 3. Tom throws a football to Wes, who is a distance L away. Tom can control the time of flight T of the ball by choosing any speed up to V maximum and any launch angle between 0 and 90 degrees. Ignore air resistance and assume Tom and Wes are at the same height. Which of the following statements is correct? A. If V maximum less than square root from dl, the ball cannot reach Wes at all. B. Assuming the ball can reach Wes at V maximum increases with the L held fixed, the minimum value of T decreases. C. Assuming the ball can reach Wes at As V maximum increases with the L held fixed, the maximum value of T increases. D. Assuming the ball can reach less as L increases with the V maximum held fixed, the maximum value of T increases. E. Assuming the ball can reach less as L increases with the V maximum held fixed, the maximum value of T increases. Solution. Here we can use kinematic formulas for this problem. First formula connects the change of vertical part of speed for time t, which is this one. And second connects range with the horizontal speed at time t. And now we can use formula sine squared theta plus cosine squared theta equal 1, which will give us this equation. And this equation we can turn to quadratic equation to t squared. Solution for this quadratic equation will give us this expression. First of all, we can emphasize that root with a negative sign are responsible for minimum time, which is for angles less than 45 degrees, and positive for angles theta equal 90 minus theta. That's a positive. And if we look at this square root, we can say that V maximum cannot be less than the square root from D over L. In that case, ball cannot reach less at all. So it means that this sentence is good. Let's go further. For negative sign, we have minimum time, and if we increase L, this root will decrease. It means that the time will increase, which is not answer for D. If we take maximum time and we increase L, this root will decrease and time will decrease, which is for answer E is good, because here we have negative answer, which is correct. So E could be correct answer. Now let's take a look for B and C. For maximum time, if we fix length and increase maximum speed, the time will increase, which is for answer C correct. It means that this is not the answer. For negative sign, we can multiply and divide this t squared by the same function, after which we can get this result, this formula. And now we can see that if we increase the speed v, we decrease minimum time, which is correct for answer B. It means that answer B is not good. So finally we can see that correct answer is D. US Physics Olympiad year 2013, F equal MA, first round. Problem number 4. The sign shown below consists of two uniform legs attached by a frictionless hinge. The coefficient of friction between the ground and the legs is μ. Which of the following gives the maximum value of theta such that the sign will not collapse? Solution. First, let's draw the picture with the forces. I just show forces on left leg. For right leg we have symmetrical forces. So on left leg we have mg, which is applied to the middle of the leg going down, We have force P, which is applied from the right leg horizontally. We have normal force, which is applied on bottom of the left leg. And we have force of friction F, which is applied to the left leg to the right. In case of static equilibrium, we have to write equations for horizontal, vertical equilibrium and for rotational equilibrium. Let's do it for horizontal equilibrium. For horizontal equilibrium to the left leg, we have to equalize force P to force F, force of friction. For vertical, we have to equalize normal force and mg. And for rotational equilibrium, we have to choose the point of rotation. In our case, that will be best point this one, where we apply force N and force F. In that case, we don't have to count torques from these two forces because they are zero. And now we have clockwise force mg and torque from this force equalized by counterclockwise torque from force P. Let's write this equation. So for rotational equilibrium we have this equation. That's a rotational equilibrium where we use that P equal F, force of friction. Now we can express force of friction from this equation. So from here we can find what is force of friction. That's this one. But we know that force of friction cannot exceed mu multiplied by normal force, which in our case equal mg. It will be critical for our case. If force of friction equal mu mg, we can put it here and define that critical angle will be when tangent theta over 2 equal 2 mil, which is answer E. Problems 5 and 6. The following information applies to questions 5 and 6. A student steps onto a stationary elevator and stands on a bathroom scale. The elevator then travels from the top of the building to the bottom. The student records the reading on the scale as a function of time. Question: at what times does the student have maximum downward velocity? Question 6. How tall is the building? Solution. As we can see from the picture, from 0 to 2 seconds elevator is not moving because reading of scales is the same as student's weight. But between 2 and 4 seconds reading is just 60 kilograms. It means that elevator going down with a constant acceleration, so velocity is increasing, and when it reach 4 seconds it's start to move with a constant velocity, because here we have reading of scales is the same as weight of student. So we have maximum velocity between 4 and 22 seconds, and after that the reading is going up. It means that elevator going with deceleration with the same amount as it was acceleration, and it reached the 0 in 24 seconds. After that it's not moving. So it means that answer for question A is between 4 and 22 seconds, which is answer C. Question number 6. How tall is the building? Now let's convert our sentences to formulas here. So first we can find what is the equation for student's motion between 2 and 4 seconds. That will be ma equal mg minus normal force. In our case, mg equal 800 newtons, normal force is 600 newtons, and mass is 80 kilograms. It means that acceleration equal 2.5 meters per second square. Now we can find what is the distance covered by elevator between 2 and 4 seconds. That will be 1/2 at1 square, which is 5 meters. Now let's count what is the speed after 4 seconds. That will be at1, which is 5 meters per second. Now let's count what is the distance covered between 4 and 22 seconds. That will be v multiplied by t2, which is 18 seconds, and total is 90 meters. And now we can count what is distance covered between 22 and 24 seconds. That will be symmetrical deceleration, same as acceleration between 2 and 4. So it means that distance here will be 5 meters. It means that the total height of this building equal 5 plus 90 plus 5, which is 100 meters. So that's answer C. Problem number 7. A light car and a heavy truck have the same momentum. The truck weighs 10 times as much as the car. How do their kinetic energies compare? Solution. Let's do by definition. Kinetic energy equal 1/2 mv square. But here we need to express it using momentum. That will be p square over 2m. And from this formula we can immediately find that kinetic energy back proportional to masses if momentums are equal. So it means that kinetic energy of the truck is 10 times less than kinetic energy for car, which is answer D. Problems 8 and 9. The following information applies to questions 8 and 9. The truck is initially moving at a velocity v. The driver presses the brake in order to slow the truck to a stop. The brake applies a constant force F to the truck. The truck rolls a distance x before coming to a stop, and the time it takes to stop is t. Question 8. Which of the following expression is equal the initial kinetic energy of the truck? It means the kinetic energy before the driver starts braking. Question B. Which of the following expressions is equal the initial momentum of the truck? It means the momentum before the driver starts braking. Solution. Question A. First of all, we can write that total work done by force of friction equal to initial kinetic energy of the truck. It means that it's equal to force multiplied by distance. And it means that answer A is correct. Let's check answer B. Here we have force multiplied by Vt. But Vt it's not a distance. To count distance we can use average speed, which is maximum speed over 2. And the correct answer would be in these units f multiplied by average speed and multiplied by time. And we see that answer B is twice greater, so it's not correct. Answer C has wrong dimensions, because here instead of distance we have distance multiplied by time, and the answer D again has a wrong dimension. That's a dimension for momentum. So it means that the correct answer is A. Question 9. Which of the following expressions is equal to the initial momentum of the truck? First of all, let's write the expression for correct momentum. That will be force multiplied by time. And let's check all answers. Answer A is not correct, it has a wrong dimension. That's a dimension for energy. Answer B is twice less than the momentum. Answer C has again a wrong dimension. Answer D has twice as much as the correct answer. And let's check answer D. Here we can use so-called average speed. In our case, average speed equals maximum speed divided by 2. And we have expression for total distance, that's x equal v over 2 multiplied by time. From here we can express time. So time equal 2x over maximum speed v. And now we can insert this time to this expression for momentum. And momentum equal force multiplied by 2x over v, which is answer E, correct one. Problem number 10. Which of the following can be used to distinguish a solid ball from a hollow sphere of the same radius and mass? Solution. So first we can say that only rotational properties can give us the difference, because it's more difficult to rotate hollow sphere with the same mass and radius than a solid sphere. And if we use B answer, measurements of the time it takes the object to roll down an inclined plane, in that case a hollow object will roll longer than a solid object, and this is correct answer. For other answers there are no difference for hollow or solid object with it. Problem number 11. A right triangle wooden block of mass big M is at rest on a table, as shown in the figure. Two small wooden blocks, both with mass small m, initially rest on the two sides of the larger block. As all contact surfaces are frictionless, the smallest cube starts sliding down the larger block while the block remains at rest. What is the normal force from the system to the table? Solution. First, let's draw all forces. On small cubes we have two forces acting on them. That's mg and the normal force n1 for left cube and n2 for right cube. Now let's write the expressions for this normal force. n1 equal mg cosine alpha and n2 equal mg cosine beta. Same force acting from small blocks to this triangle block. And now we just need to count what is vertical part of this normal force acting on this triangle. We have n1y equal mg cosine square alpha and n2y equal mg cosine square beta. But because we have right triangle, we have cosine beta equals sine alpha. It means that the total force from two blocks on this triangle block in vertical direction equal just mg. It means that total force from triangle block and the two small blocks on table equal small mg plus big mg. That's the answer C. Also, we can count what is the horizontal force from these small blocks on this triangle block. Left block pressing in direction x equal with a force mg cosine alpha sine alpha, and right block pressing with the horizontal force mg cosine beta sine beta, and because cosine alpha equal sine beta and sine beta equal cosine alpha, so we have a total force equal 0. It means that we even don't need to hold this triangle block. It will stay automatically. Problem number 12. A spherical shell of mass big M and radius r is completely filled with a frictionless fluid, also of mass big M. It is released from rest, and then it rolls without slipping down an incline that makes an angle theta with the horizontal. What will be the acceleration of the shell down the incline just after it released? Assume the acceleration of a free fall is g. The moment of inertia of a thin shell of radius r and mass m about the center of mass is I equal 2/3 m r squared. The moment of inertia of a solid sphere of radius r and mass m about the center of mass is I equal 2/5 m r squared. Solution. Here we can use an energy approach. Suppose that this sphere travel distance with a height difference h, and in the end the velocity of this sphere equal v. We can count what is total speed in the end using energy conservation. Total potential energy of this system 2mgh converting to kinetic energy, which is translational kinetic energy 1/2 to mv squared plus rotational kinetic energy of this shell, which is 1/2 to 3rd r squared omega squared. But because this shell rolling without slipping, we have omega equal v over r. And finally, total kinetic energy equal 4/3 mv squared. And from here we can find that v squared equal 3/2 gh. But from other hand, we have expression for motion which connect speed, acceleration, and distance. We have v squared equal 2ad, where a is acceleration and d is distance. In our case, distance equal h over sine theta. Now we can put this expression for v squared, and we have v squared equal 2ah over sine theta. Finally, we can equalize these two velocities, this v squared and this v squared, and we have acceleration equal 3/4 g sine theta, which is answer B. Problem number 13. There is a ring outside of Saturn. In order to distinguish if the ring is actually a part of Saturn or is instead a part of the satellites of Saturn, we need to know the relation between the velocity v of each layer in the ring and the distance r of the layer to the center of Saturn. Which of the following statements is correct? Solution. First, let's investigate how is velocity depend from radius in each case. Suppose that we have this layer part of Saturn. In that case, we have velocity equal omega r, and it's definitely proportional to radius r. In case of this ring is part of satellite system, we have centripetal acceleration, which is v square over r, must be equal to acceleration due to gravity, which is g mass of Saturn over radius square. It means that v square back proportional to radius. And let's use these two dependencies for our answers. Answer A. If v proportional to r, then the layer is part of Saturn. That's true, because v proportional to r. B. V square proportional to r. That's not true in any case. C. V back proportional to r. That's not true in any case. D. V square back proportional to r. This is true if this is a satellite system, but here we have part of Saturn, which is not correct. And E. V proportional to r square. This is not true in any case. So correct answer is A. Problem number 14. A cart of mass m moving at 12 meters per second to the right collides elastically with a cart of mass 4 kg that is originally at rest. After the collision, the cart of mass m moves to the left with a velocity 6 meters per second. Assuming an elastic collision in one dimension only, what is the velocity of the center of mass of the two carts before the collision? Solution. In the system of center of mass, we have collision during which two masses collide with velocities, and after collision they move with opposite velocities with the same amount as before collision. So it means that if first cart move initially at 12 meters per second to the right, and after collision 6 meters per second to the left, it means that in the system of center of mass we have this relation, that initial velocity of the first mass equal opposite velocity for this mass after collision. And solution for this equation is v center of mass equal 3 meters per second, which is answer B. Problem number 15. A uniform rod is partially in water with one end suspended, as shown in the figure. The density of the rod is 5/9 that of water. At equilibrium, what portion of the rod is above water? Solution. Let L be the length of this rod. X is part of this rod above the water. S is cross-sectional area of this rod. Rho0 is density of water. Rho equal 5/9 Rho0, that's the density of this rod. And we have to find what is X, part of the rod above the water. Also, let's theta be the angle between the direction of this rod and the horizontal. Now we can write the equilibrium equation for rotation of this rod around this point of attachment. We have force of gravity, which is applied to the middle of this rod, and we have buoyancy force from water, which is applied to the middle of the portion of the rod under the water. And let's write the equation for this torques equilibrium. For torques, we have this equation: L as rho, which is mass of rod, multiplied by G, which is force of gravity acting on this rod, and we multiply it by L over 2 cosine theta, which is a level arm for this rod compared to this point of rotation. And that must be equalized by torque from buoyancy force. And buoyancy force equal mass of this water, which is dismissed by rod L minus x multiplied by S, and rho 0 multiplied by G, and we multiplied it by level arm for this buoyancy force compared to this point of rotation, which is 1/2 L plus x multiplied by cosine theta. After all cancellations, we have this expression, and x equal 2 over 3L, which is answer D. Problem number 16. A very large number of small particles forms a spherical cloud. Initially they are at rest, have a uniform mass density per unit volume rho 0, and occupy a region of radius r0. The cloud collapses due to gravitation. The particles do not interact with each other in any other way. How much time passes until the cloud collapses fully? The constant 0.5427 is actually a square root from 3 pi over 32. Solution. This problem is about dimensional analysis. And here we already have in the expression square root from G rho 0 in denominator. So we can represent answer in form of time equal this expression, and we have to find what is power alpha. Let's represent our parameters using dimensional analysis. Here we represent all dimensions for all parameters, like time is t power 1, gravitational constant has this representation, density has mass power 1 over L cube, and the radius is L power 1. Now we can put this expression to this equation. Now our equation look like this, and from here we can find what is the alpha. For distance dimension we have this equation. It means that alpha equals 0, and the correct answer is D. Problem number 17. Two small equal masses are attached by a lightweight rod. This object orbits a planet. The length of the rod is smaller than the radius of the orbit, but not neglectable. The rod rotates about its axis in such a way that it remains vertical with respect to the planet. Is there a force in the rod? If so, is it tension or compression? Is the equilibrium stable, unstable, or neutral with respect to a small perturbation in the angle of the rod? Assume this perturbation maintains the rate of rotation, so that in the co-rotating frame the rod is still stationary but at an angle to the vertical. Solution. Let's analyze this motion. Because the gravitational force goes as back proportional to r square, the inward force on the inner mass is greater than the inward force on the outer mass. On the other hand, both masses have the same angular velocity, so the centripetal acceleration goes as proportional to r, and the outer mass must be subject to a greater centripetal force than the inward one. So the rod must exert an inward force on the outer mass and an outward force on the inner mass. Thus, the rod is in tension. Second, the stability of the position is best understood in the coordinating frame. In this frame, the outer mass experienced an outward radial force and the inward tension of the rod, and the inner mass experienced an inward radial force and the outward tension of the rod. When the rod is rotated slightly, these forces create a restoring torque, so the equilibrium is stable, and the correct answer is B. Problem number 18. 2 point particles, each of mass 1 kg, begin in the state shown in the upper left corner. The system evolves through internal forces only. Which of the following could be the state after some time has passed? Let's analyze these pictures. So here on the first picture we have total momentum is 0, center of mass is not moving, and we have rotational momentum equal 2. Let's analyze other pictures. Picture A. Here we have a center of mass is in other point, not 0, 1. It's in point 0, 0. So that's not good. Picture B. It has non-zero momentum. It's no good. Picture C. It has angular momentum less than angular momentum in the primary picture. Picture D. It has angular momentum greater than initial angular momentum. And picture E, it has the same position for center of mass. It has 0 momentum, and it has same angular momentum. So the correct answer is E. Problems 19 to 21. The following information applies to questions 19, 20, and 21. A simple pendulum experiment is constructed from a point mass M attached to a pivot by a massless rod of length L in the constant gravitational field. The rod is released from an angle θ0 less than pi over 2 at rest, and the period of motion is found to be t0. Ignore air resistance and friction. Question 19. At what angle θg during the swing is the tension in the rod the greatest? Question 20. What is the maximum value of the tension in the rod? Question 21. The experiment is repeated with a new pendulum with a rod of length 4L using the same angle θ0, and the period of motion is found to be t. Which of the following statements is correct? Solution. Question 19. At what angle θg during the swing is the tension in the rod is greatest? So first let's draw this picture for this pendulum. On this pendulum we have two forces acting. It's a tension T and gravitational force mg. And let's angle will be theta between vertical and this rod. Now let's count what is the tension would be in the process of this motion. We know that if pendulum going by circular motion, we have centripetal acceleration, which is normal acceleration, and tangential acceleration. In our case, the main thing is normal acceleration, and it's equal to v square over L. And let's write the equation which produce this acceleration. So we have mv square over L equal tension minus part of force of gravity in the direction of this rod, which is mg cosine theta. Second, we have to find what is v square, and this we can find using energy conservation. So we have potential energy, which is mgl multiplied by cosine theta minus cosine theta 0 equal 1/2 mv square. And from here we can find what is mv square over L. That will be this expression. And now we can put this expression to the first formula, and finally we have for tension this formula, that tension equal mg multiplied by 3 cosine theta minus 2 cosine theta 0. And this function has a maximum when cosine theta equal 1, which is for theta equal 0 degrees. That's answer B. Question 20. What is the maximum value of the tension in the rod? We just answered this question in the previous 19. That was from this formula, and if cosine theta equal 1, we have tension equal mg multiplied by 3 minus 2 cosine theta 0, which is answer E. Question 21. The experiment is repeated with a new pendulum with a rod of length 4L, using the same angle theta 0, and the period of motion is found to be t. Which of the following statements is correct? Solution. We know that for small angles we have a formula for period equals this function. But for big angles, this formula is not correct. And from dimensional analysis we can find that period must be equal to this expression, where function f from theta 0 approximately equal to pi for small angles, but it's different for other angles. And if we look at this formula and we increase the length of the rod 4 times, we increase the period 2 times, which is answer A. That's correct answer. Problem number 22. A simplified model on the foot is shown. When a student of mass m equal 60 kg stands on a single toe, the tension T in the Achilles tendon is closest to solution. As we can see from this picture, we have to count balance around the point of rotation, which is ankle joint. We have normal force from toe, which is equal mg of student. It's going counterclockwise, and we have tension in Achilles tendon, which is going clockwise. They have to equalize each other. So we have equation. Tension multiplied by a distance 5 centimeters, this one, That's equal mg multiplied by distance 25 cm, which is this one. From here we can find that tension equal 5 mg, which is 3000 newtons. That's answer E. Problems number 23 and 24. The following information applies to questions 23 and 24. A man with a mass m jumps off of a high bridge with a bungee cord attached to his ankles. The man falls through a maximum distance big H, at which point the bungee cord brings him to a momentary rest before he bounces back up. The bungee cord is perfectly elastic, obeying Hooke's force law with a spring constant K, and stretches from an original length of L0 to a final length L equal L0 plus small h. The maximum tension in the bungee cord is 4 times the weight of the man. Questions. Question 23. Determine the spring constant K. Question 24. Find the maximum extension of the bungee cord small h. Solution. Let's use information from this condition. First, we can write equation for energy conservation. When a man traveled height big H down, he used potential energy mgh, and this potential energy turned to potential energy for stretched spring, which is 1/2 k h small square. That's the first equation. Second equation is about maximum stretch of this cord. We have force of tension, which is kh equal 4 times mg. Now let's divide the first equation by second equation. This will give us that small h equal 1/2 big H. And the last step, we can put this small h to the second equation and find that k equal 8 mg over big H. Let's check the answers. Answer E is good. Answer D is twice less. Answer C is 8 times less. Answer B is 2 times less. And answer A is 4 times less. So correct answer is E. For the question 24, we already found the answer, that small h equal 1/2 big H, which is answer A. Problem number 25. A box with a weight W will slide down a 30 degrees incline at constant speed under the influence of gravity and friction alone. If instead a horizontal force P is applied to the box can be made to move up the ramp at constant speed. What is the magnitude of P? Solution. First, let's do free body diagram. Here we have incline with angle theta 30 degrees, and the forces acting on our block during the motion up is mg, which is force of gravity, force P, which is horizontal force of friction, which is going this way, and normal force. From the first sentences we can find out that coefficient of friction equal tangent theta, because this angle is critical for this kind of friction. When body is moving with a constant speed, means that our angle is critical, and tangent theta equal mu. Next step, let's find what is a normal force. From this picture we can find that normal force equal mg cosine theta as usual, plus force P multiplied by sine theta. Next step is to find what is force of friction. Force of friction equal mu multiplied by normal force, or this expression. And last step is to make equation along this incline. Along this line we have P multiplied by cosine theta must be equal to force of friction plus part of gravitational force in this direction, which is mg sine theta. And finally, this is the expression for P cosine theta. And now we can express force P using this equation through this formula. We use mg equal W. We divide numerator and denominator by cosine theta, which will give us expression through tangent theta. We use knowledge that mu equal tangent theta, and after that we have this expression, and the tangent theta equal 1 over tangent theta, which is 30 degrees, equal 1 over root 3, and finally we got root 3 W. That's the answer, D.